Hey guys, Ms. Winters here. Hope you guys are doing well and have had a good Father's Day today. The second part of this video is talking about Rolle's theorem. Okay, Rolle's theorem. Suppose that y equal f of x is continuous at every point on a closed interval ab and differentiable at every point on its interior open interval ab. If f of a equals f of b, then there is at least one number c in the open interval at which f prime of c equals 0. In essence, what this is saying is if you have a curve, okay, and it's continuous and from this point to this point and differentiable in all the interior points, and this y value here is the same as this y value here, then clearly for it to go up and come back down, for there to be the same y value, there has to be a horizontal tangent. Okay, that's what Rolle's guarantees us. All right, again, you need continuous differentiable and you need f of a to equals f of b, which means it has to curve in some way and either come back down or curves upward, either way, but you would have to have a horizontal tangent. F prime of c is that equals 0 is that horizontal tangent. All right, and we can see right here we have one horizontal tangent. Over here we have our A and our B. We have three of them. So it guarantees that there is at least one of those horizontal tangents. Okay, now clearly if it's not continuous and differentiable, then it may not have one. For example, here's the next one here. Here's A to B. All right, well, it is not continuous and differentiable here because at A itself, it's not continuous. Okay, and same thing here. There is an interior point where it's not continuous. All right, now here it's continuous, but it's not differentiable on an interior point, on this x naught point. Why? Because this is a cusp. If you recall, a cusp can have an infinite number of tangent lines at that point. Okay, so it would not hold up there. Okay, so basically, there may be no horizontal tangents if the hypotheses of Rolle's do not hold. Okay, so there may or may not. It's possible that there may be no horizontal tangents. What Rolle's does is guarantees us that if it does hold, then there will be. But if it doesn't hold, then there may or may not. Okay, that's what it's telling us. All right, hypotheses, I made a note here, are basically if-then statements. If this, then that. If these conditions happen, then you get that. All right, so here I made some notes here you might want to jot down because it kind of summarizes what I just said. Here's Rolle's theorem. If your function is continuous on the closed, differentiable on the open, and if f of a equals f of b, which means on this interval, your y values, remember these are x values, your y's are the same, then the result is there exists a c that's an element of the open interval ab such that f prime of c is 0. That's what Rolle's guarantees us. Okay, and here is a type of problem that you would see in your homework. You may be asked to verify Rolle's theorem for a particular function on a closed interval. So how do we do that? Well, first of all, you need to make sure that all of the three conditions are met in order to verify Rolle's theorem. All right, well, f of x, is it continuous on this closed interval? Well, sure, it's a polynomial. Polynomials, by definition, are continuous functions, okay, with a domain of all real numbers. So f of x is continuous on the closed interval, -2 to 2. Second one, is it differentiable on the open interval? Is there any point where it would not be differentiable here on the open interval from -2 to 2? Well, no, there's no point where it wouldn't be. It's differentiable everywhere. Okay, so f of x is differentiable on the open interval, -2 to +2. And then finally, 3. All right, does f of a equal f of b? Okay, f of -2, does that equal f of +2? Question mark, question mark. Well, it certainly should, because as you notice here, The two terms that we have are variable terms, and both of the powers are even. This is an even function, which means it is reflected about the y-axis. All right, think of a quadratic. They're going to have this. They will have a point with the same y values. So yes, definitely check. You can plug it in to verify that. Okay. Now the next part here is to verify that f prime of c equals 0 has at least one solution in the open interval -2 to 2. Okay, so in other words, we're going to take our function, we're going to find f prime of x, all right, and we're going to set it equal to 0 and see if there is a value here. Can we solve for x? That value that x would be our c. Okay, well, let's find f prime of x. That would equal, let's see here, that's going to be 4x cubed minus 2x. And of course, we're going to set this equal to 0. All right, well, let's go ahead and factor. What can I factor out here? I could factor a 2x, which would leave me with 2x squared minus 1 equals 0. All right, I have a variable here, so you have to set it equal to 0 as well. So 2x equals 0 implies that x equals 0. And then we have 2x squared minus 1 equals 0. Well, that would give me 2x squared equals 1. All right, so I'm going to divide both sides by 2 and then square root it, which means x would equal plus or minus the square root of 1/2. We need to determine, well, what is approximately the square root of 1/2? All right, well, using your calculator, for this you could approximate this between 0 and 1. I mean, think of it this way. 1/2 is between 0 and 1. The square root of 0 is 0. The square root of 1 is 1, which means the square root of 1/2 has to be between 0 and 1. Okay, so as it happens, and you can verify this, it is approximately, because it is irrational, 0.7. Okay, plus or minus 0.7. Well, what I'm going to do now is say, do any of these x values fall within this interval between negative and positive 2? Well, sure, they all do. 0 is certainly between a negative and a positive number. Plus or minus 0.7, that's between negative and positive 2. So then I would state that since 0, positive 7, and negative 0.7, negative positive 7, positive 0.7, my bad, are within the open interval -2 to 2, then I would simply state all conditions of, you write that in, of Rolle's are satisfied. Boom. Proved it, tombstone it, there you go. All right, and that's all you'll be asked to do with Rolle's theorem. All right, so hopefully between my video and my good friend Dr. Robinson's video, this will make a lot of sense to you. This is a pretty short, sweet, and to the point section, so hopefully you guys will do well in the homework, and the next video will be coming tomorrow. And again, as I posted an announcement, I will give an extension on this homework because this did come out awfully late in the day that you were supposed to watch it. Okay, because it was Father's Day and I was out of town seeing my dad. Anyway, hope you guys had a great day today, and we'll chat soon. Bye-bye.